Hello friends, I am Snehal and I am teaching you physics. In last lecture, we had started with a motion in a straight line and we also plotted some position versus time graphs. We tried to read them. In today's lecture, our job is to do velocity versus time graphs. So let us start. Now we are going to use a lot of analogy with last lecture. So let me just plot some position versus time graphs. Now for object at rest, the position versus time graph is like this. Try to recollect. And for object in uniform motion, the graph is like this. Now we are going to plot velocity versus time graphs. So first graph I will plot is for the case of uniform motion. Okay, so velocity on this vertical axis, time on horizontal axis. Now observe in this first graph where object is at rest, so something is constant and the thing which is constant is position. So x is constant. Now you can observe that when position is constant, this graph starts from this point, x0, the starting position, and the graph is parallel with the time axis. So similarly here, this graph will start at this position, this velocity u, which is starting velocity or initial velocity, and here velocity is constant. That's why this graph will be parallel to the time axis, just like this. Here position is constant, in this case the velocity is constant. So the velocity versus time graph for the case of uniform motion is going to be parallel to the time axis, starting from the starting velocity or initial velocity. Okay, so next graph we'll plot is for the case of uniformly accelerated motion. And again, we'll use analogy. So velocity versus time graph for the case of uniformly accelerated motion. Now we know that velocity is change in position, delta x divided by delta t. And you can observe in this case, the velocity is constant. So change in position is constant. Okay. So object is moving with uniform velocity, then its position versus time graph is like this. It's an inclined line. Slope of that line gives you velocity. So similarly, I can write acceleration is equal to change in velocity divided by change in time. And this is the case of uniformly accelerated motion. This was case of uniform velocity. So by analogy, I can plot a graph for uniformly accelerated motion. It will start from this velocity, just like this graph started with this starting position. This graph will start with the starting velocity and graph will be like this. So slope of this graph will give us this uniform acceleration. So you can see by using merely analogy, we plotted the velocity versus time graphs for the case of uniform motion and for the case of uniformly accelerated motion. Now let's carry this analogy further. So let me erase this. Okay, let me just keep this here, position versus time graphs. And suppose we have any random position versus time graph. Random is something like this. So let's choose some time interval and let's recall that in this time interval, let's say from t1 to t2, the average velocity is given by v average is equal to x2 minus x1 divided by t2 minus t1. And how do we find x1? So it's from this point we draw a perpendicular onto this position axis. So this is our x1, and from this point we get x2. Okay. So average velocity is x2 minus x1 divided by t2 minus t1. And we also know that it is slope of this line. If we just join the end points of this curve, then slope of this line gives us average velocity. Similarly, if I take velocity versus time graph, v versus time graph, and this is any random v versus t graph, the information I get from this graph is acceleration. So this is time t1, this is time t2, this is position, this is velocity at time t1, v1, and here velocity at time t2 is v2. So if I want to find acceleration, and now this is average acceleration, so a suffix av is for average, is equal to v2 minus v1 divided by t2 minus t1. So we can write this as delta x divided by delta t, and here we can write this as delta v divided by delta t. And it will also be the slope of this line joining these 2 points, which corresponds to uniformly accelerated motion. But remember, in this case, acceleration is uniform for case of this rate line, for this rate plot, and acceleration is not uniform for the case of this curved line or the curve, black curve. But the average acceleration, which is also uniform acceleration in case of this red line, is equal to average acceleration for this black curve. So we can find out average acceleration from velocity versus time graph in the same way we found the average velocity for the case of position versus time graphs. And then next thing we found was instantaneous velocity. Now recall what is instantaneous velocity. We just denote it by v, and we write it like this: limit delta t tends to 0 delta x over delta t, meaning the time interval is very small, that is the velocity at a particular instant of time. And we write it compactly like this: dx by dt, and we call it derivative of position with respect to time. Now bear with this term derivative. I am aware that I have just defined derivatives and I have not shown you a way to find derivatives. That we'll do in later lectures. So just bear with this term for some time. And just now, this instantaneous velocity, we know that it is given by limit delta t tends to 0, which means that the time interval is very, very small, so small that is almost 0. This thing will remember. Then the change in position with respect to change in time gives us instantaneous velocity. And suppose we wish to find instantaneous velocity at this instant, let's say t, then we also know that it is slope of this tangent line at that point. Okay, so for now this much will be enough. So similarly, if I wish to find instantaneous acceleration, I can represent it like this. A is the instantaneous acceleration at any time, so it is limit delta t tends to 0, delta v over delta t. And what will that thing be? It will be the derivative of velocity with respect to time. For the sake of definition for now. And what will this thing be in this graph? So graphically it is, suppose at any point t, any time t, it is just slope of this line, tangential line. The slope of this tangential line at that point, tangent line, gives us acceleration. Okay, so this is very important point, and I have also drawn a bracket over there. This is also important thing. So slope of position versus time graph at any point gives us instantaneous velocity. Similarly, the slope of velocity versus time graph at any point gives us instantaneous acceleration. So this is average acceleration, this one is instantaneous. Good. So now these velocity versus time graphs are more useful than you might think. We found that slope gives us something. Now, if we try to find area under the curve or area under those graphs, we'll get some more information. So let us see what kind of information we get from area. So let me erase this. And now we'll be dealing with velocity versus time graphs only for some time. So let me just draw this simple graph. For the case of uniform motion, this is suppose initial velocity, or let me just write v here because it's not changing, so I need only one letter. Okay, so this is velocity versus time graph for the case of uniform motion, and we know that velocity is given by, suppose particle starts from some position x0 and then it goes to some position x. So for the case of uniform motion, I can write v equals to x minus x0 divided by t minus t0, and let's take t0 equals to 0. So let's take t0 equals to 0. So I can write this as t only. Okay, t minus t0, x minus x0 divided by t. Then now this is t0 equals to 0, and let's take some point. Let me call this t only. Now if I take this t on other side, what do I get is x minus x0, that is the displacement, s is equal to x minus x0 and if I take this on other side, I get v into t. You have to observe here that v is this side and t is this side. So what will be v multiplied by t? It will be area under this v versus t graph, so this shaded area. Okay, so what does this shaded area gives us? It gives us displacement. So we got something new here, some new information. We know that slope of velocity versus time graph gives acceleration, and area under the velocity versus time graph gives displacement. So we come to know about all type of information, all kind of information which we will need for the case of motion. So remember that this velocity versus time graph is more important, or it's more useful than the position versus time graphs. And it's simple to find out information from the velocity versus time graphs. We'll try to generalize this. So before that, let me write this statement somewhere. The statement is area under velocity versus time graph gives displacement. That is change in position. Okay, this is very important, so we are taking note of that. Okay, now in last lecture, we also found this first kinematical equation. First kinematical equation of motion, and we know that this equation of motion is v equals to u plus at. Okay, so now we'll see derivation of next two kinematical equations of motion by using velocity versus time graphs. So for that, we are interested in the particular case of uniformly accelerated motion. So let me write derivation of kinematical equations of motion from Vt graph there is another method to derive these derivations, this kinematical equations of motion, that we'll see in later lectures. That is the method of derivatives and integrals. But before that, let us study this method. So let me draw this graph, velocity versus time graph, for the case of uniformly accelerated motion. And let's limit this graph up to this point. So this is my starting velocity, u is the initial velocity. Let's take v as some final velocity, and t is time. Okay, that means initial or starting time t naught is equal to 0. Let me just draw this line, and this is final velocity at time t. So this is v. Okay, so now we know that slope of this velocity versus time graph gives us acceleration. So we can derive our first equation, the kinematical equation of motion. We know that slope of v versus t graph gives acceleration. So using this, in time t, I can write a equals to v minus u divided by t. So at time t equals to 0, the velocity was u. At time t equals to t, the velocity is v. So slope of this graph gives us acceleration. So v minus u is equal to 80 and v equals to u plus 80. So this thing is very trivial. After that, we just found that the area under this velocity versus time curve gives us displacement. So we are going to use that. Now let me just represent this trapezium by A, B, C, D. And I can write that area under VT curve gives displacement, and using this I can write displacement in time t is equal to the area of trapezium ABC. Now we need to know the formula for area of the trapezium. Even if you don't know the formula, there is another trick. You can just break this trapezium in two parts like this. Then you can find out area of this rectangle, and you can add area of this triangle to it to find the area of trapezium. But because I know the formula, I am going to use it, and it is simpler this way. So area of trapezium is half of sum of parallel sides multiplied by height. Okay, so if I just tilt this trapezium by 90 degrees, it will look like this. Okay, concentrate here. I have tilted it by 90 degrees. So this side, this much is u. This much is v. And these two are the parallel sides, and this t is height. Okay. So I can write here the parallel sides. U is represented by this side, so it is half of length of the side AD plus length of the side BC multiplied by height, which is the length of side DC. So length of DC. Okay. After that, let's just substitute. This is U, the length of side AD is U, this length is V multiplied by the time is T. So displacement is equal to half of U plus V multiplied by T. Okay, then let us call this equation 1, and let me call this equation number 2. Now I will rewrite this here and I will erase this. So S equals to half of U plus V multiplied by T And from this equation, or let me just write A equals to, we know v minus u divided by t. This is the equation for acceleration. We'll just take t on other side and a on this side. So this equation gives me t equals to v minus u divided by a. I will just substitute this here. So what do I get? S equals to half of u plus v or v plus u multiplied by v minus u divided by a. I substituted for time there. Now I will take 2 and a on other side, and we know this formula, a plus b multiplied by a minus b equals to a square minus b square. Using that formula, I can write 2 times a multiplied by s is equal to b square, okay, minus u square. So v square minus u square equals to 2as. This is another kinematical equation. So this is actually the third kinematical equation. Okay, we wanted to find second. Okay. Now, this was equation number 2. So, from equation 2, we can find second kinematical equation 2. I will substitute in place of v, that v is equal to u plus at. So, let's see what do we get. S equals to half into u plus v. We know it is u plus at. I have substituted for v here, multiplied by this t. So this is very simple. 2u, okay, this is half of 2 times u plus u into this t. I will take the t in bracket, so ut plus at multiplied by t is at squared. Now dividing by this 2 throughout, we get s equals to ut plus half at squared. This is kinematical equation number 2. This is second kinematical equation. Okay, so I found third kinematical equation before the second. It doesn't matter. Now we'll just collect these kinematical equations and write them at one place. So kinematical equations of motion are first, second and third. I will write now in order. So first one is v equals to u plus at. Second is s equals to ut plus half at square, and third equation is v square minus u square equals to 2as, or you can write this as v square equals to u square plus 2as. And let's not forget that s is equal to x minus x naught, so whenever needed we can substitute it. Okay, so these are kinematical equations of motion. They are very important, so we have taken note of them. Now let me just plot last graph for this lecture, and that is the acceleration versus time graph. And we are going to attempt only one of these, and that one is for uniform acceleration. So here acceleration is constant, acceleration is a, just like we did with the position versus time graphs and the velocity versus time graphs. Here acceleration is constant. Now what kind of information do we get from the acceleration versus time graph is that we know that acceleration is given by v minus u divided by time. So suppose acceleration is uniform, final velocity is v, initial velocity is u, and t is the time. Then if I take t on other side, I get AT equals to v minus u, and suppose we take some time here. Now just see that this A is length of this side, T is length of this side. So A multiplied by T is the area of this rectangle. That is the area under acceleration versus time curve gives us change in velocity. Okay. So the information we get here is area of AT curve gives us change in velocity. Okay, so now we are done with this plotting of graphs, and we obtained some information from the graphs. So let me just try to collect the information at one place. So first information we get from position versus time graph is the slope of xt graph at any point or at any time gives velocity at that time. Similarly, second thing is slope of Vt graph at any time gives acceleration, the instantaneous acceleration. This is instantaneous velocity. I have mentioned that at the time. So slope of Vt graph at any time gives acceleration at that time. Then we have area under the Vt graph or area under Vt curve gives displacement or the change in position, and next one is area under acceleration versus time curve gives change in velocity. Okay, so this is the essence of whatever we did in these two lectures. In next lecture, we will see some problems based on motion in a straight line, some simple problems. Till then, you also can try some problems. Thanks for watching the lecture.